Hello, welcome back to the Honors Precalculus COVID-19 inspired video series for Mr. Billingham's class. Again, a couple of you have told me you like these videos, so I will continue to produce them. Today we're going to work on using tree diagrams to find probabilities and conditional probabilities, and that should complete section 1. We used tree diagrams back in chapter 9 as a way of visualizing the multiplication principle of counting. Tree diagrams may also be used to solve probability problems. Consider the following problem. Two identical cookie jars are on a counter. For the purpose of the problem, imagine you cannot see into them. Jar A contains 2 chocolate chip and 2 peanut butter cookies. Jar B contains only a single chocolate chip cookie. A jar and then a cookie are selected at random. What's the probability we wind up with a chocolate chip cookie? Well, since there are a total of 3 chocolate chip cookies out of 5 total cookies, you might think the answer is 3/5. You'd be wrong. Let's take a look at this with a tree diagram. In this diagram, we show every possible route to selecting a jar and choosing a cookie. We can either choose jar A or jar B at the beginning. Once we've opened jar A and we reach in, we could pick up the first chocolate chip, the second chocolate chip, the first peanut butter, or the second peanut butter. If we'd selected jar B, we would have only had one choice, and that would have been a chocolate chip cookie. You can fill in probabilities for each of the arms of this tree. For instance, choosing jar A or jar B, those are each 50%. Once I've chosen jar A, I have a 25% chance of getting each of the 4 cookies. And in jar B, I have a 100% chance of getting its cookie. Here is the chart with the probabilities filled in. To get the probabilities at the far right, we use the multiplicative principle of probabilities. Since there is a 1/2 chance of choosing jar A and a 1/4 chance of choosing the first chocolate chip cookie, the probability of that pair of events, choosing jar A and then choosing the first chocolate chip cookie, is obtained by multiplying 1/2 times 1/4 to get 1/8 or 0.125. To finish the problem, we now say that if we want to get a chocolate chip cookie, that can only happen a few different ways. It can happen that way, or that way. And the probabilities are 0.125, 0.125, 0.5, which adds up to 0.75, or 3/4, or 75%. So the probability of getting a chocolate chip cookie is 75%, not 3/5. Let's revisit Sal and Val and the vanilla cream chocolates using a tree diagram. Val initially picks a chocolate. It can either be vanilla cream or non-vanilla cream. The probability of it being a vanilla cream is 4 out of 12, or 1/3. The probability of a non-vanilla cream is 8 out of 12, or 2/3. The second choice can happen to be either another vanilla cream or a non-vanilla cream. And that can happen in either of the first 2 choices. The probability of a vanilla cream after you've already got a vanilla cream, we've removed one of the 4 vanilla creams, so there are 3 of the remaining 11 that are vanilla creams. So this probability is 1/11. which we got before. A non-vanilla cream, there are 8 non-vanilla creams left among the 11. So this probability is 8 elevenths, and 1/3 times 8 elevenths is 8 33rds. If I got a non-vanilla cream, then there are 4 of the 11 left that are vanilla creams. So this branch would have a probability of 4 elevenths, and 2/3 times 4 elevenths is 8 33rds. And if I got a non-vanilla cream followed by another non-vanilla cream, the second non-vanilla cream, only 11 of the remaining 12, only 7 of the remaining chocolates are non-vanilla cream. So this is 2/3 times 7 elevenths, which is 14 33rds. If I get a common denominator up here, 1 11th is 3 33rds. So my total probability of all of the n's, 8 33rds and 8 33rds is 16 33rds, plus 14 33rds is 30 33rds, plus 3 33rds. They add up to 33 33rds, which is 1, as any good probability function must do. I can use this tree diagram to answer other questions. For instance, what's the probability Val got at least 1 vanilla cream? Well, that would be here, here, or here. So I can calculate this a couple of different ways. I can add up 3 33rds and 8 33rds and 8 33rds, getting 19 33rds. Or I can say if he didn't get at least 1, the opposite of that is he got none, and that would be here. So I could also have done 1 minus 14 33rds, which is again 19 33rds. Let's go back and look at a Venn diagram again, showing two events that have some overlap. Here I show what I just described. I have an event A and an event B, and their intersection is A intersect B. I want to ask the question, what's the probability that A happened given that B happened? So what is the probability of the following? Since we know B happened, we know that we're inside the blue circle. The only way that A happens inside the blue circle is if we're in the intersection A and A intersect B. The way we write this out is with the following formula. This is the formula for conditional probability. The probability of A given B, that's how we pronounce the expression on the left, or P of A given B, is the probability of the intersection of A and B divided by the probability of B. Let's revisit the problem of the chocolate chip versus peanut butter cookies being drawn from the jar, and let's apply the conditional probability formula to figure out the probability that a cookie came from jar A given that it was a chocolate chip. Here's our tree for that problem again. So again, I'm looking for what's the probability that we took a cookie from jar A given that we wound up with a chocolate chip cookie. Using our formula, I let event A be that jar A was selected and B be the cookie is chocolate chip. And I'm looking for the probability of A given B, or jar A was selected given that the cookie is chocolate chip, and it's equal to the probability of the intersection that it's jar A was selected and it's chocolate chip divided by the probability that it's chocolate chip. And I can calculate these from my chart. Here I've marked off the 2 items that are in the intersection of A and B, that jar A was selected and we came up with a chocolate chip. And they are 2 with probabilities of 1/8 and 1/8, which add to 1/4. In red, I've checked the 3 items that wind up being event B, that the chocolate chip cookie was selected, and the total probability of those is 1/8 plus 1/8 plus 1/2, or 1/4 plus 1/2, or 3/4. Therefore, the probability that jar A was selected, given that a cookie was a chocolate chip cookie, is 1/4 over 3/4, or 1/3. So this is a very useful technique for finding conditional probabilities. We'll now apply conditional probabilities in an interesting case which is somewhat topical, but it's about HIV instead of coronavirus. But you can easily imagine it being about coronavirus. Here's some information as of the year 2009. Turns out the probability of an adult in the United States having HIV/AIDS was about 0.006, or about 0.6%. There's a test known as the ELISA test, which is used to detect the virus antibody in blood. If the antibody is present, the test reports positive with a probability of 99.7%, and gives a false negative with a probability of 0.3%. If the antibody is not present, it reports a false positive with a probability of 1.5%, and negative with a probability of 98.5%. Sounds pretty good, right? Let's do a tree diagram for this. My first branch is whether the antibody is present or absent. We'll assume that anyone with HIV/AIDS would have the antibody present. From the data, 0.006 have the antibody present, which means that 0.994, or 99.4% of the people, do not have the antibody. At this point, the test either comes out with a positive or a negative result. The information tells us that if the antibody is present, which is the top pathway from the beginning, it has positive results with a probability of 0.997, which means that if the antibody is present, it will test negative with a 0.003% chance. The information further tells us that if the antibody is not present, which is the lower branch, the test reports positive with a probability of 0.0015, and reports negative with a probability of 0.985. This is all as expected. If the antibody is present, you want a positive result most of the time, and if it's not present, you want a negative result most of the time. Let's get the final probabilities at the end. I've done these separately on a calculator. I've filled in the numbers obtained by multiplying the probabilities along each path. You can check if you want, I did. The probabilities all add up to exactly 1, as they must. So the first question we want to ask is, what's the probability of a positive test result? That can happen in 2 different ways. And that probability would be 0.005982 plus 0.01491. So the probability of a positive result is about 20%. So what do you think the probability would be that a person actually has HIV/AIDS, given they got a positive result? The answer is a little bit surprising. So the math shows us that if a person gets a positive test result, the probability that the antibody for AIDS is actually present, in other words, that they're actually infected with HIV/AIDS, is only 28.7%. And that means that more than 70% of people who get a positive test result for AIDS using this particular test actually do not have it. and have to go on for a further, more accurate test. This concludes the fourth video for 10.1 and concludes 10.1 itself. So stay well and look forward to other videos and other postings soon.